In the last lesson, we learned about intermolecular forces and how, depending on how strong they can affect surface tension, boiling point, melting point, and vapor pressure. In this lesson, we're going to start getting into how we can predict if those intermolecular forces will be strong or weak. In other words, when we're looking at molecules, what will cause them to have stronger intermolecular forces than another compound. And really what it comes down to is it comes down to the type of intermolecular force they have. So we're going to be learning about three types of intermolecular forces: hydrogen bonding, dipole-dipole interactions, and London dispersion forces. Now there are a couple more than just these, but we're going to start with these because these are the type of intermolecular forces that exist in covalent compounds. And since we're using the term molecule in intermolecular forces, we are talking only about covalent compounds. Now later on in the unit, we're going to get to, well, what about ionic substances? But here we're primarily talking about covalent compounds, and these are the three types of intermolecular forces that exist. Depending on the type they will have either stronger or weaker intermolecular forces. So you can see I have this little up arrow here, which indicates that if we see a molecule that we later on identify to have hydrogen bonding intermolecular forces, it's likely that that is going to have stronger intermolecular forces, and therefore it's going to have much higher boiling points and melting points. The vapor pressure is going to be very low, right, because the molecules stick together well. This trend where London dispersion forces are the weakest of the forces, though, is only a trend. Because if you think of hydrogen bonds as like, say, for instance, well, let's get rid of me. Say, for instance, the strongest of the intermolecular forces, that doesn't mean that the London dispersion forces are something that can be ignored. As a matter of fact, if you have lots and lots of London dispersion forces, they may as a group turn out to be stronger than the one strong hydrogen bond. I like to think of London dispersion forces as kind of like the Lilliputians, in Gulliver's Travels. The Lilliputians were very small. They were puny, right? And therefore, they didn't have a lot of strength. But when they worked together, they had no problem tying Gulliver down. And it's sort of the same thing here, right? Is that if you have lots and lots of London dispersion forces, they could turn out to have more intermolecular forces total, and they may actually have higher boiling point compounds than something that just has hydrogen bonding. But all things being equal, usually if something has hydrogen bonding, it will have the highest boiling points. So I'm just putting that out there because you will notice exceptions to this trend, but that's the general trend. Okay, so we're actually going to start in the middle. Do you see where dipole-dipole interactions? We're actually going to start in the middle here and work our way out to the other two. And today we're not going to get to hydrogen bonding. We're not going to get to London dispersion forces. As a matter of fact, we're starting in the middle because if you understand dipole-dipole interactions, then the other two become much, much, much easier. They're much shorter. So we're not even going to finish dipole-dipole interactions today. Our only job today is for you to figure out when a dipole-dipole interactions will occur in pretty much two atom situations, right? Really small molecules. Okay, so here's an example of what I mean. Dipole-dipole interactions, you can see why they're called dipole-dipole interactions, because if you have a polar molecule, so like, just focus on just one HF, well, if there's a big separation in charge, and if you've never seen this little sort of music note, which is a delta, it means there's a partially negative charge on this end, on the fluorine end, and a partially positive charge on the hydrogen end. And you can imagine that turns them into like little magnets, where the positive end of one will be attracted to the negative end of the other. So that's called a dipole-dipole interaction because this separation of charge is referred to as a dipole. Matter of fact, we very often in chemistry, let me get a nice pen color here, will draw a dipole arrow pointing in the direction of electron flow. And that arrow often would go like this on this end. So I would say the dipole is this way on this one. Why the little cross in the end? Because you can see that it represents the positive sign, that's the positive end, and the arrowhead represents the flow of electrons towards the other end. So whenever you have a polar molecule, it will create this partial separation charge. I mean, it's not ionic, right? It's not like sodium and chlorine where we get full-blown positives and negatives where the electrons were flat out given to chlorine. Here we have a sharing of electrons that's a bit uneven, and fluorine has them more of the time. Therefore, fluorine will be partially negative and you have a polar molecule. So anytime you have a polar molecule, it will have dipole-dipole interactions with another one because they're both polar molecules. Kind of seems a little bit redundant, but this is one dipole, that's the other dipole, and this is the dipole-dipole intermolecular force between them. So if we can identify a molecule as being polar, then we can decide that it has dipole-dipole interactions, and we know that's a fairly strong interaction. Well, at least it's stronger than London dispersion forces. So what makes a bond polar? Well, let me get rid of my pen and ink here. What makes a bond polar is when two atoms share electrons unevenly. That means they have a polar bond if that's true. The way I like to think of it is, I like to think of it, when my girls were really little and they'd be embarrassed by me talking, that's not actually a picture of them, but when they were really little, sometimes we would buy them a Christmas present that was to be shared between the two of them, and that sharing was very, very uneven, right? This girl over here is like the fluorine, and this girl over here is like the hydrogen, right? They're not going to be sharing evenly because she looks a lot older, right? And so this thing that they're trying to share is going to spend more of its time around the older girl than the younger girl. But, occasionally the older girl might be like, oh, look, there's a bunny over there. And then you can see the younger girl come in and take the toy, and it will spend part of its time over here. So if you were to watch a map of where the electron is, it spends most of its time around this atom. And occasionally over here when the other one gets interested in a bunny rabbit, but then the older one will come back and steal it, right? And the electron spends more of its time over here, but then it spends occasionally a little bit of time over there. So this atom is what we refer to as a very electronegative atom, right? Whenever you have a large difference in electronegativity between these two atoms, it makes the bond polar. Now, of course, if you had two older kids, right, two fluorines, well, they're going to share pretty darn evenly between them because they're sort of, equally strong in their pollen electrons. And of course, if you had two young kids, they would also share pretty evenly. It's the large difference in electronegativity that really matters here. This, by the way, these are both referred to as nonpolar bonds. So a large difference in electronegativity between two atoms will cause a bond to be polar. This is the Pauling electronegativity chart. So you can see that hydrogen and fluorine have very different electronegativities, pretty large differences. Of course, if you had lithium and fluorine, they would have an even greater difference in electronegativity and be even more polar. But any difference in electronegativity will cause a bond to be at least somewhat polar. So electronegativity is atoms with high electronegativity have a strong pull on the electrons in the bond, and fluorine definitely is the most electronegative. Now, I find most of the time when we're answering questions about electronegativity and polar bonds, we're not given this Pauling electronegativity scale. We need to work based on general patterns, which is as you go more to the right, electronegativity increases, and as you go more up, electronegativity increases. But you can see there are a lot of exceptions in the middle especially. So it's just the general trend usually we're working on. All right, so let's do a little bit of, if we know that we have to have a polar bond in order to have a dipole-dipole interaction, I'm asking you here which of these bonds would be polar. But of course the other way to say to them is which of these bonds would form a dipole-dipole interaction with another bond just like it. Because you got to be polar to have a dipole-dipole interaction. Well, let's start with the ones that can't. They will not form a dipole-dipole interaction because they're not polar. I think definitely this one is nonpolar, right? Two chlorines will have the same electronegativity. Any others that you see that would be nonpolar? I see the phosphorus, that would be nonpolar. So these two could not have an intermolecular force of dipole-dipole attractions to other atoms. But all the rest of these could to a certain extent. Now, if we were doing it based on general patterns, if you look at a periodic table, you'll notice that nitrogen is more to the right and more up. So I might be tempted to say it would be the more electronegative atom, and the electrons would flow towards the nitrogen, and it would be more partially negative. That symbol would be partially negative, this end would be partially positive. So when we're doing these, I want to draw a dipole arrow and put in partial positives and negatives. I need that little delta because if I'm not, then I'm talking about, like, say, for instance, sodium and chlorine. There, the difference in electronegativity is so much that no longer is there a sharing of charge, and that partial would be inappropriate. Ionic substances are the most polar of all, but here we're focused on covalent substances. This one would be nonpolar covalent, so with that one over there. These would be polar covalent. This one, definitely there's going to be a difference in electronegativity. It would be polar covalent. This one over here we're going to come back to at the end. We've already seen these two, difference in electronegativity, so it's polar covalent. And same goes here. Now let's get the dipole arrows on each one of these, and then at the end we're going to talk about the carbon and hydrogen. If I bring up the electronegativity chart, you can see, let's start with HCl. H has an electronegativity of 2.2, chlorine has 3.6. Clearly chlorine is more electronegative. The dipole will flow towards the chlorine. What about between these two, oxygen and sulfur? Well, oxygen is more electronegative than sulfur. And it fits the pattern. It's more up and to the right. So I'm going to say the dipole is going to flow that way, towards the oxygen. This end would be positive because it has less electrons. This end would be negative. They're still sharing, but not very evenly. Now let's look at carbon and hydrogen. Hydrogen has an electronegativity of 2.2 and carbon's 2.5. Yes, it is true that carbon is slightly more electronegative than hydrogen, and so you would expect to get a slight positive and a slight negative charge. But hydrogen's a bit unusual. You can see based on its number, it's almost like hydrogen needs to be somewhere right over here if it were going to follow the pattern. So whenever carbon is attached to hydrogen, we generally speaking consider that those two are so close in electronegativity that we would refer to that as a non-polar situation. And you'll see that this idea of hydrocarbons being nonpolar plays a big role later. Now, if you don't have an electronegativity chart, and a lot of times we're going based on trend, remember the more to the right and the more up you go, the more electronegative the atom would be. And if we were going to pick two, like say for instance, we haven't done IBR, look at these two. These two are so close in electronegativity that even though I think bromine is more electronegative, it's not much more electronegative. So the iodine is going to be a little bit positive and a little bit negative. Versus if I had IF, now there's a bigger difference in electronegativity. I might want to draw a bigger dipole vector, right? Because that's really what that's supposed to represent. And now the separation of charge is going to be quite large. This one would not only be polar, it would be more polar covalent because there's a bigger difference in electronegativity between its atoms. So you can imagine if there was another one near it, it might have a slightly different interaction. So let's look at this idea here. If I have this drawing that I made at the beginning of HF interacting with another HF and forming a dipole-dipole intermolecular force, we know that if I were to draw, say, chlorine and chlorine, that those two would have no dipole-dipole intermolecular force between them because those are nonpolar molecules. Now that doesn't mean that they don't have any intermolecular force between them, but it's not going to be dipole-dipole. That's not an option for them. But for IBR it is. And if we were going to draw this interaction, what I'm really asking you is, how do these hook up? Which ends will be attached to each other? And which will be positive and which will be negative? Well, if I draw an IBR, and I draw another IBR, well, I'll do that in just a second. Let me label this first. According to our electronegativity chart, bromine is more electronegative. I'd expect the negative end to be down here and the positive end to be there. So, of course, you can imagine that bromine would be attracted to the iodine because its negative end is going to be attracted to the positive end on iodine. So we know which end will be partially positive and partially negative, and we'll know how they'll sort of organize as each other as they pass by. But I don't want you to lose track of the idea that these interactions, these intermolecular forces that are dipole-dipole forces in this case, they're very temporary. They come and go. If I were to look at these two and I were to decide why does this molecule have weaker intermolecular forces than that one, well, it has to do with the strength of their dipole-dipole interactions. Remember, we said that the dipole difference between these two, because there was a bigger difference in electronegativity, caused there to be a huge separation of charge. And so you can imagine that that interaction, I got it right. That interaction would be very, very strong, that dipole-dipole intermolecular force. But over here, hydrogen and chlorine on the electronegativity chart, let me see if I've got it. I do have it. Hydrogen and chlorine are much closer in electronegativity than hydrogen and fluorine. So maybe I'll draw my vector a little bit shorter because it's not as big of a separation in charge. You're going to have a small positive here and a small negative. And so that it's almost like they aren't as magnetic, right? If you have north and south poles. So this dipole-dipole interaction will be significantly weaker. So in summary, for two molecules to interact by dipole-dipole intermolecular forces, they must be polar. Definitely, they have to be polar. If they're non-polar, they will not have the ability to have a dipole-dipole intermolecular force. Now that naturally makes you wonder, okay, since Jones told me yesterday that all molecules have intermolecular forces, what kind of intermolecular forces do those have? Well, we'll get to that, but it's going to take us another lesson to get to that. And the reason is because, well, look at this. What about larger molecules? If I were to say to you, yes, I know that two carbon tetrafluorides are going to have some kind of intermolecular force between them because all molecules do. Just like these two will have some kind of intermolecular force. Will that intermolecular force in each case, will it be a dipole-dipole interaction? And the answer is, for SF4, yes, it will be a dipole-dipole interaction. But CF4, no. It turns out it will be a London dispersion force interaction. Why? Why is it that CF4 can't interact with another molecule like it using dipole-dipole interactions? Well, the reason is obviously because it's a nonpolar molecule. It can't do dipole-dipole interactions, whereas this one is a polar molecule. Now, I think you know where we're going from here. If in order to identify dipole-dipole interactions, which are significantly stronger than London dispersion forces, we're going to need to know if bigger molecules are polar. And in order to figure that out, we're going to need to be able to draw their Lewis structure and then use that Lewis structure to figure out the shape. Now, we've done this before, and at this point you may be feeling super confident in that from CP, or maybe you're not feeling so confident. And so that's where we're going next, is how do I draw a Lewis structure and how do I turn it into a 3D model that will help me see the shape? And how can that shape tell me if the molecule is polar or not polar? But that's for the next lesson. Great job today.